Jose Hernandez is going to speak to us about dynamic time warping with physics-informed constraints, the idea of mapping the water injection signal to the production signal to be able to understand connectivity in the subsurface. Jose, go ahead, take it away.
Okay, so hello, my name is Jose Hernandez and I am working with Dr. Michael Pyrcz. So today's presentation is dynamic time warping for well injection and oil history connectivity characterization. So the agenda for today's presentation is first, I'm just going to give you an executive summary, the motivations of this project. Then I'm going to present the project's goal. Finally, after that, I'm going to give an explanation about the proposed physics constrained dynamic time warping method. Then I'm going to discuss some results. And finally, I'm going to give you the key points and some future work. Basically, the motivation for this work is that water flooding is one of the most important and mostly used secondary methods for oil recovery. However, one of the challenging with water flooding is that it's very challenging to do well location optimization because of the influence of the different injector wells and other producing wells into the producing wells. So basically, thinking of that problem, we're proposing a novel using intuitive physics constraints method to dynamic time warping algorithm to basically detect the influence of the water injection into the oil production response. And we are going to do this by mapping the input water signal into the oil production response signal. When we create this mapping of the two signals, then we can determine a lag time. So that lag time is basically the influence or the time that it takes the water to reach one point or to affect the oil producing well. One of the advantages of this method is that we don't have to make any assumptions about the data. We can just work with our production and injection data. And also, well, this method is robust in the presence of noise and is very flexible, so it can be applied to other applications like enhanced geothermal or for environmental remediation. The goals for this project, so first we start using the classical dynamic time warping for this application, and we identify some shortcomings for this method. So one of the shortcomings is that when we perform the classical algorithm, we have backwards alignment in time. So basically, we were matching points of the injection signals that were like passed in time. So that is not possible for our case because we want to find points that are or matches in future in time. So that was one of the limitations of the classical method. Another problem that we found is that we generate singularity matchings. So that means that multiple points were matched to a single point in the response signals and vice versa. While this may be true in geological settings, for fluid flow, this is not something that we want to obtain. So that was another shortcoming. Another problem that we find here is that the classical method matches every point of the injection signal into the response signal. And that causes some problems because we know that we have surface operations and sometimes the readings might have some noise. So we don't want to match all the points from one signal into the other signal. So we needed to find a way to limit that portion of the classical method. And additionally, we know that we have attenuation and diffusion effects at the reservoir level. Therefore, we know that we are going to have some attenuation and diffusion effects. So that means that our projected mapping has to have some degree of attenuation in our projections. So based on this analysis and in these limitations of the classical method, we propose some constraints to avoid these shortcomings so we can find an optimal match between the two time series. Well, the proposed method it basically consists of 6 steps. The first step is basically to some normalization of our signals, and we have to do normalization because we don't want to generate some bias because of the different orders of magnitude between the water injection and the oil production data. After we have normalized our data, we have to construct a cost matrix. So this cost matrix is just the distance between all the different points between the two signals. And this is going to be the basis of our algorithm. After we have construct our cost metrics, we have to construct a cumulative cost matrix. And this cumulative cost matrix is where we are going to implement the constraints, and it is when we are going to define, or we are going to find, the optimal warping path. After we can constructed our cumulative cost matrix, we have to define what is going to be the starting point of our warping path. And to do that, we just perform a global minimum optimization of the end row of the proposed of the cumulative cost matrix. And after that, we perform dynamic optimization recursively from the starting point until the end of the sequence to find all the points that belong to the optimal warping path. And in this case, we have proposed two additional hyperparameters that are alpha and theta, and these are going to help us to control for the search space limitation, to construct our search space. So this is just some graphics of our method. So here we have the normalized, an example of a normalized water injection and oil production response without any noise. So this is just two noise-free signals. So as I mentioned before, the first step was to construct our cost metrics between the two signals. So this is just the distance between each single point from the two signals. Once we have constructed our cost metrics, we have to generate the cumulative cost metrics, which is basically these metrics at the bottom. So these metrics has implemented some constraints. For example, this region here that is in white. So all these values are set to infinity. So when we perform the dynamic optimization, we don't fall in this region, because this region is going to generate to have these problems of matching points that are backwards in time. This plot on top of here basically is going to tell us where is the beginning of the warping path. So basically this value here is just the cumulative cost at the end row of the cumulative cost matrix. So once we perform the minimization, we find the lowest point in this line, and this is going to be our basically the starting point. And once we have defined the starting point, we have to perform recursive optimization to find the subsequent points of the warping path. So in this case, we have multiple options, right, to find the optimal warping path. But this path especially is the one that has the lowest cost, and therefore it has the highest similarity between our injection signal and our response signal. That is basically the oil production, and the injection signal is basically our response signal. The two hyperparameters that we have are called alpha and theta, and these are going to help us to restrict the search space at each iteration during the recursive optimization. And to find these two hyperparameters of the optimal values of these hyperparameters, basically we evaluate different evaluation metrics. We have the cost, the mean square error, and the cosine similarity. But we're going to find, or we're going to select the pair of hyperparameters that not only have the best accuracy metrics, but also retain the highest number of match points in the sequence. And these are going to help us to determine what are the optimal values for alpha and theta. And in this case, theta is basically an amplitude angle. So basically, it's going to restrain our search space at iterations. And alpha is going to tell us what is the size of our search space. So in this case, if we have our starting point at this location, basically the allowed search area and by which we can find the next point of the warping path is going to be delimited to only the gray area inside of this region that is delimited by alpha and theta. The other constraint that we have here is basically we are skipping to find points in the horizontal and vertical columns, and we are doing this to avoid to generate the singularity matching of the signal between the two signals. So basically, this is going to be our allowed search space at each iteration. And we have some physics meaning about these hyperparameters. So basically, theta is an amplitude of the search space, and this can be related to the advection and diffusion effects of the reservoir. So basically, we're telling the algorithm you cannot find points that are very far away from your starting point because this is something that we don't want to. And alpha is the size of the search space, as I mentioned before. And this can be related to the heterogeneity scale of the reservoir. If we have a very homogeneous reservoir, then we're going to have a smaller alpha value, as opposed to have a larger alpha value for more heterogeneous reservoirs. Some results. So here, so this is the same case that I showed you at the beginning for the classical dynamic time warping, but in this case, we're using the constrained version of it. So in this case, we avoid all the shortcomings of the classical algorithm. So the first time, we don't have more singularity times between the two signals. And additionally, we are only looking, or we are only matching sequences that are similar at later times. So we are looking for similar patterns that are after the water injection has happened. Additionally, we are not matching every single point as opposed to the classical algorithm. So this is going to help us to determine the lag time between the water injection and the production response. So we evaluate also the different levels of noise that this algorithm can handle and can let us to find an optimal warping path. So basically, we define or we identify that there's after some level of noise, the method becomes unstable, and we have more uncertainty on the selection of the starting point of the warping path. And we observe that this basically this algorithm becomes unstable at around 0.9 signal to noise ratio. And that happens basically because when we add more noise to our signals, we have a shift in the global minimum of the selection of the starting point of the warping path. And that shift is generated because of the random noise that is added into the signal. And since this is basically the starting point, the algorithm is going to start building, or is going to find the warping path based on this starting point. So here the red line is just the signal-free, the noise-free signal, just as a reference. So you can see the impact of the noise with a reference case. And in this case, this is a stable case right before it becomes unstable. So you see that this level of noise is also making an impact on the warping path, but there is not much a significant difference of the case when we have a pure signal without any noise. And this is basically the optimal alignment between the two time sequence, which is unstable and which is unstable. So you can see when it's unstable, it's going to match a subsequent signal of that is a suboptimal result of the warping path. And in the case of stable, that it also finds the similar pattern as the noise-free case. We also evaluate the time length ratio evaluation. So in this case, we're measuring, or we are evaluating how long or what is the length of our signal, so we can find a representative match between the two signals. And we find also that there is at some point that the method becomes stable, and it becomes stable because and basically there is not enough information to obtain a satisfactory match in future. And we can observe that because in this case, basically these two time series are almost the same size. So this is around 90 points in time, and this is 125 points in time. So since we don't have futures in points, then the algorithm, and because of the constraint, it's just going to generate one-to-one match because it's just making, it's finding the optimal points along the border between the constraint and the search space. And we have here a case when the method is like right before the method becomes stable, just to see the difference between the two, the boundaries. So here is what I was mentioned to you, that when we have an unstable or a time length ratio greater than this value, then we generate just one-to-one matches. That this might not be very helpful or representative to find the lag time of our water injection into the production response. And this is basically the optimal alignment when in the point right before the boundary between where the method becomes stable and unstable. And here we still have a match between the two signals. Finally, we also test this algorithm using production field data. So here we select two wells that were close to each other and in an isolated region of a reservoir. So we have a water injection period of 36 months and an oil production period of 132 months. So when we evaluate the time to learn ratio, this is a time to learn ratio of about 0.27. That is below our threshold, by which the method becomes so stable. So the first step, well, we perform the algorithm, we determine the starting point of the warping path, and then we perform the dynamic optimization. And we select, we perform hyperparameter tuning. So basically here the red box indicate the location of the optimal hyperparameters that has the highest or the best evaluation metrics while retaining the highest number of match points. So at the end, we select a hyperparameter alpha equal to 4 and a hyperparameter equal to 32. And this is the final optimal alignment between the two time series in the field production data. And here, using this optimal warping path, we can make an estimation of the mean lag time between the two time series between the water injection and oil production to be around 58 months. And we also can estimate what was the water breakthrough time. That was around so we can just estimate the water breakthrough time around this point here. So some of the key points for this presentation is that basically the implementation of physics constraints to the classical dynamic time warping algorithm can allow us to determine basically the effect or the influence of the water injection time of the water injection into the oil production response. We also identified that this algorithm is robust with noise up to 0.90 signal to noise ratio, and we also determine the optimal ratio of the lengths of the two sequences or the two time series to determine a significant match between the two. We propose a methodology to select the optimal hyperparameters alpha and theta to determine the hyperparameters, the optimal hyperparameters. At the end, well, the final optimal warping path can be used to estimate the expected lag time between the water and the oil production signal, as well as the breakthrough time. And in this method, it's only using production and injection data. So we know sometimes data is difficult to acquire or it's expensive. So this is available, easy to get data. So the next step for this project or for this research is to investigate the influence of several injector and production wells at the same time instead of using pairwise wells. Also, like we were thinking, if bottom hole pressure is available, this method is flexible, so it can work not only with oil production water injection signals, but with any type of signals that we have. So we can use these other type of signals to find or reduce the uncertainty in the estimation of the water breakthrough and the lag time estimates. So at the end, or the final goal is that we want to characterize our reservoir using lag times, and also finally generate a predictive modeling to estimate the lag time at unknown locations of the reservoir, so it can help us to determine optimal water flooding or new wells, well location optimization. Thank you so much for your attention, and if you have any questions, I will be happy to answer those.
Jose, thank you very much for your presentation. Appreciate that. I think this is a very interesting idea. We are not the first to use dynamic time warping in the subsurface. Many who have used it for stratigraphic stratocorrelation between wells. And what we recognize is that that wouldn't work for this problem, because we know, there they can have unconformities, things can just, their truncations. That doesn't happen with flow signals. And so Jose's done a great job incorporating that. Okay, we have a question here from Tomo. Thank you very much for the question, Tomo. Can you interpret any physical meaning on gradient of warping path?
The gradient of the warping path? Well, I think like the gradient of the, that's a very interesting question. I think like the gradient of the warping path is going to give us an indication of basically the amplitude. So it's like we're looking at the attenuation effect here, because if we have a larger warping path, that means that our points are more spread on the response signal. So basically, if we have a very stiff warping path, that means that we have like a short front of the water injection front. But if we have like a more elongated warping path, that means that our response signal is getting matched in a lower sequence into the all response. So that means that our water is having more problems to travel through the reservoir. So I think that might be one interpretation for the slope or the gradient of the warping path.
Okay, awesome. And anybody, if you've asked the question, you want to ask it yourself, go ahead. Brian, did you want to just jump in? Or I can just ask it right here. Please, can you redo the explanation of warping path for someone who doesn't know the term?
Yeah.
Do you have the elevator pitch for warping path?
I think I do. So warping path, that means that we are, okay, so this is a warping path right here. So basically a warping path, it's like we're going to warp our time series. So we're going to match two time series that are different in time and length. So basically what we're doing, or what this warp time is doing, is to find a subsequence inside of the longest sequence that has the highest similarity between these two signals. So basically we're going to find what is this warping band is like. It's like a half point between this signal and this signal that has the highest similarity. So that's like the connection between, the warping point is basically the connection between the two signals, like at which locations or at which points we're going to find a similar signal into your response signal. I think that will be one of my definitions.
Okay, so from what I understand, it's a mapping from the input signal to the output signal. It's a mapping of the input time to the output time that maximizes correlation. Does it have to be linear or monotonic, or I mean, surely it has to be monotonic because of causality, but presumably it's not constrained to be linear, is it?
Exactly, no, and it's one of the advantages of this method, that, because most of the methods to evaluate water injection rely on the data is linearly correlated. So in this case, this warp band is completely free, so it doesn't have to be a linear correlation. It has the flexibility to match signals that are not linear in time or speed.
Yeah. Just another quick question, quick general question about these techniques, if I may, moderator.
That's fine, Brian.
I mean, don't you often find that that when you look at real well production histories, the most obvious features, and therefore the ones that machine learning techniques tend to latch onto, are the ones caused by operational events? You know, somebody swung the wrong valve or pressed the wrong button, you get a huge spike or step in the production history, and your pattern matcher or whatever algorithm gloms onto that feature and ties everything to it. Just general comments on that, if you would.
Yeah, exactly. So that was, we also thought about that. So at the beginning, the classical algorithm was matching every single point from one signal into the other. But we were aware of that scenario. So that's why we decided to generate an algorithm that is not matching all the points. So it's just matching the general trend. So even though we have maybe a spike, that might be an outlier because someone pressed the valve or opened the valve and we have a spike in production, then the algorithm is just going to ignore that one because it's not going to have the highest, it's not going to have the lowest cost as compared to other future points in time. So that's one of the things that we implemented with the constraint.
And Brian, thank you very much for the questions. Jose, thank you very much for the great presentation.